Okay, hi everyone, and welcome to the first of the lab through read-throughs for this term, and the first for Data Science 1. Now, I'm actually going to skip over the first couple of these, and basically just sort of start off with the labs that deal with some of the new functions that we need to use this term. So with that in mind, I'm going to go through Lab 3 today. So Lab 1 didn't have a script at all, and Lab 2 was reintroducing some of the techniques we used in the first term. Now, this script, Lab 3, explores something called Bernoulli trials and the binomial distribution. And to do that, we use a family of three different functions, all of which have this binomial suffix and then a different letter at the beginning, denoting a slightly different way to use this, but they all use the same mathematical logic, and we'll go through what that is. Now, a Bernoulli trial is any random experiment with two outcomes, and we model those outcomes as the number 1 for success and the number 0 for failure. And of course, one way of thinking about this is like flipping a coin. So if heads is success, tails is failure, we have two outcomes and a probability for each. Now, in this case, a coin flip, the probability is generally assumed to be 50-50. But actually, Bernoulli trials can be any random experiments, even if the chances of success and failure aren't equal. And that's actually something that we can modify with these functions as well. And we're going to look at that further down. So let's look at the first of these functions then. So we can see this starts with an R, and in this case, this stands for random. So random binomial, and we have 3 parameters here that we set. And all of the functions we're going to look at today, they all have these 3 parameters. Well, they all have 3 parameters. And in fact, these latter two, size and probability, this isn't going to change. But we're going to have other things we can set other than n. Now, I'm just going to run this function a few times just so we can see what it does. So the outcome is going to come out down here in the console. And you can see this generates either 0s or 1s, and it does so at random. Although we'll talk about what random means in the context of this in a little bit. Now, if we try and visualize this then, the best way of thinking about it, and this is going to be something that you've probably looked at before at some point, is these kind of probability trees. So we have 2 outcomes, is a 1 and a 0. Our probability of each is 0.5. So that's our coin flip. And in this case, that would be an n of 1. Now we'll come back to this because this is, I think, a useful way to visualize this. Okay, so what if we generated more of these? Because we can increase the n here. So if we visualize that, our n of 2 is going to be just this, but twice. So we have these 2 independent instances of 1 coin flip, 2 coin flips. What if we change this to 10 though? Let's see what the answer we get is. Okay, so there's our outcome. So we've got 3 1s, 2 0s, a 1, and 4 0s. Now, just to briefly explain what this is. So computers can't really generate truly random data. So obviously they have to have a starting point, and then they generate some kind of calculation that spits out the 1 or the 0. And it does so over time with this probability. What we can actually do, though, is we can set that random starting point, or rather we can set that arbitrary starting point is a better term for this. So if we run this, you can see here's the outcome. And no matter how many times we run this, we're going to get the same result. It'll only change, actually, if we change to a different seed that we set. And again, it will generate the same outcome. That said, if we run this entirely without this, we can see this is going to generate different random numbers every time. So if you want to generate slightly counterintuitively, the same set of random numbers, we can use set seed. If not, we can generate this. Now, you can see here across 10 iterations, none of these are exactly balanced. We're not getting 50% ones and 50% zeros. And this is because ultimately, although in that case, actually, that was the last one, that was 5 and 5. But in our original example, let's look at 1, 2, 3, 4, 5, and run that again. And if we create a bar plot here, we can see we've got, that time, quite a lot more ones than zeros. This is some code that puts this into a data frame. We'll come back to this later. But let's look at what happens if we increase this size parameter even more. So there's no way I can visualize this, right? I'd need 100,000 of these individual coin flips. But we can generate it really easily using R. So here I'm generating 100,000 coin flips, keeping these the same, particularly probability here. So this probability of 0.5, this is 50-50. This is always the probability of success. If we run this, we're going to see, really no matter what we set the seed to, so I can change that again, we're always going to get exactly the same outcome, because across 100,000 iterations, there's never going to be any difference in the aggregate results. The individual results will be different though, and you can see if you looked at the top corner of the screen here while I was running that, the exact order of ones and zeros will be different, but the aggregate outcome will be just the same. Now, again, I'm going to skip over this, so we're just using nframe here to put this in a data table. I can run this quickly just to show you what this looks like. And indeed, I'm getting not finding function because I have forgotten to run tidyverse. Let's come up here, get tidyverse loaded. There we go, that's loaded up now. Now I can use nframe. I can put this in a tibble. And I can use ggplot on this now. ggplot will tend to work better with an actual data frame. Okay, so that's this parameter then, n. We can increase the size, the number of individual coin flips. Probably the more interesting thing to change, though, is this parameter, size. So n and size sound kind of similar, but the structure here is quite different. So let's go back to here. Now, if we increase instead the size to 2, what we're looking at is something more like this. So now we have sequential coin flips. So we flip that coin twice, and we track the outcomes across these. So we've got a 1 here and a 0 here, 1 here and 0, 1 and 0. And our probabilities stay the same across both. So we've got 0.5, 0.5, 0.5, and so on. Now this means that we can actually have different outcomes here. We're not just dealing with 1s and 2s anymore. So if I flip a coin twice, I get heads twice. My overall outcome is a 2. If I flip it once and get a heads and once and get a tails, overall is 1. And likewise 0 and then a 1 leads to a 1. And 2 zeros here leads to a 0 overall. So I've now got 3 different outcomes I can achieve here. And of course, if I keep increasing the size, we've got to think that it keeps coming further out this way. This keeps just increasing out in this direction. So I'm actually going to change this to So we're going to have an n of 1 here and a size of 2. So exactly what we just looked at here. And a probability of 0.5. We're not going to use this for a second. Let's just look at this as just the pure function. So 1, 2, 1, 0, 1, 2, 0 again. So there we go. We've got 3 possible outcomes. Now, what are the probability of those outcomes, though? Because probability is set to 0.5, but this is about each iteration. And what we actually need to do is we just need to calculate this along these individual branches. So all this is of course 0.5 times 0.5, and that equals 0.25. And this is then the same across every branch. So we've got same here, same here, and the same again here. So my individual outcomes then are all the same. So 0.25 on each branch because they're all 0.5 times 0.5. Now the difference though is that, well, these outcomes are the same. This both leads to a 1, which means that in other words we can combine these two probabilities. So actually my probability of a 1 is 0.5. So actually we've got unbalanced probabilities here. So this, in the center here of this distribution, has a higher, what we call probability density. So I'm going to get more 1s than I'm going to get 2s or 0s because there's more ways to get to a 1. Now what this means over a large number of iterations, so let's increase this to 1,000, but I'll increase that here. We're going to go up to 100,000. Size of 2 and a probability of 0.5. Let's see what that looks like. So there we go. So we've got this graph here. Now, in fact, this is because our probability density is 0.5 here, 0.25 there, and 0.25 here. And that's not what's on our x-axis because this is the number of flips. So actually this is about 50,000 and around 25,000 for each of those, if I've got that right. But you can see it follows the probability density. Now, what that means is then we can model for any number for size here, though. So let's see what happens if we instead, let's change the size to 10. So we have 10 sequential coin flips. Now, this gives us any outcome from 0 to 10. So 11 different distinct outcomes. If we run this then, and remembering that just as 1 had a higher probability, so the numbers closer to the center of this outcome range are also going to have higher probability densities. So if we run this, what we'll see here is this distribution emerging. Because there are lots of different ways to get to 5, just like there were lots of different ways to get to 1. Slightly fewer ways to get to 4 or 6, but still quite a few. And out here, there's only really one way we can get to 0 or we can get to 10, because we'd have to flip those coins 10 times in a row as heads or tails. Now, this doesn't mean that we won't get anything in here, because there are 0s and 10s here across 10,000 iterations. But it's always going to be proportionately much smaller to these numbers where we have lots of different pathways that take us to 4s, 5s, 6s. So that's what our binomial does. But as we've seen, because this is just a product of this basic kind of calculation, actually we don't need to generate random numbers in order to be able to do this. In fact, we can just calculate this directly from the probabilities. In other words, we can use the logic that we use here directly. We don't need to generate the data. And this is what our second function is going to do. So you can see here we've changed that R to a D. And now we've got a option here called X. So let's see what happens here when we run this. So 0.24, and it'll stay that way every time. So there's nothing random here. This is a calculation that will always stay the same. Now, what does this mean? Well, 0.24, so about 1/4. We transferred it into a percentage. Well, let's look at our random data. So 5, we've got about 25,000 out of 100,000. In other words, 25% of our answers. For 4, it's a bit lower than that. So let's have a look at 4. There we go, about 20, about 1/5 rather. So what does that translate to 100,000 flips? Well, about 20,000. So really what we're doing is just directly returning the probability of these outcomes, rather than having to generate data in order to see this. Now, of course, we can also do this for a range. So we use ranges in R. We can create this object, which is a range from 0 to 10. So these are our outcomes. And then we're using that X to put into this formula. So we create X here and use it here. Now, if we put that into a binomial distribution, and I forgot to run the X, let's run all of that. We're going to see exactly the same shape, because whether we actually flip the coins or we just do the calculation, what we call the probability density isn't going to change. And on this graph, you can see the probability density directly mapped here. And just to illustrate this, let's change it back to our original graph. So here we go, we're going to have size 2. Our outcomes range from 1, no they don't, they range from 0 to 3. And let's see how that looks. So there we go, there's our binomial distribution. Oh no, they range from 1 to 2, that's why it looks strange. Let me just correct that. So 0 to 2, and we've got our plot that we looked at earlier with these higher probability densities in the center. So no matter how much we increase size, if we wanted to, let's also increase that size to 200. Our range of outcomes would now be 0 to 200. However we do this, you can see here, that's going to generate the same basic data. This is a bit small. There you go. My figures, margins are too big here even. Okay, so there's only really one more thing we might need to do now. And let's try having a look at it here. So I'm going to restore this to where it was before. So I think we had 0 to 10 for D binomial, the size of 10. Let's run that again. There we go. Well, what we could think is, well, what if, rather than knowing the individual likelihood of, say, getting 5 heads and 5 tails, or 4 heads and 6 tails, what if we wanted to know the collective likelihood of getting 4 or less? Well, again, we can do that pretty easily because we have another function here. Now, to do this, though, again, it's not complex in terms of the mathematics, because what if, for example, here, we were interested in the collective probability of getting 2 or 1. So all we'd have to do is, well, we say, what we're interested in is actually the joint probability of all of this, which of course means rather than just summing the same outcomes, we sum all of these. So our outcome then would just be 0.75. And we could do that the other way as well. And with larger distributions, we can sum whatever we want. But all of these outcomes, so these three, have to sum, the bottom of the column here, to 1. So we can always subtract one outcome from 1 and get the probability of the rest, or sum these together and get the joint probability of all of them. Now what allows us to do this is p-binomial. So in this example here, we've got 4 and less. This is the blue area we're interested in. And if we run that, q equals 4, we can see that's 0.37. Again, though, let's try it with our example that we've been using. So here's our q. So we're going to have a q of, let's say this is q of 0, let's say. And our size is 2. So that will return the outcome 0.25. And if we want the inverse of that, so this is what we actually calculated, we just have to subtract this from 1. So 1 minus p-binomial q of 0, size of 2, 0.75. So exactly what we see here. So in that case, we just calculated this, the q of 0, and we subtracted it from 1, and that gives us, again, 0.75. Now, there's only one more thing we haven't looked at here, and that is what happens if we change the probability. So let's go and have a look back at this. So all we've got to do if we want to change the probability is just change the probability of success and failure, and carry on calculating in the same way. So let's do that on a fresh sheet here. So let's say this time we're going to specify we're interested in the p-binomial of, let's say, let's get d-binomial of a range, shall we? So we're going to have d-binomial and let's say our the range we're interested in is, let's say, yeah, so it's 0 to 2, isn't it? Actually, that should be, let's try that again. So this should be d binomial x equals 0 to 2, size equals 2. But this time, let's set the p here, let's do a p, to 0.2. So my probability of success is now 0.2. So let's model this out. So here we've got this same tree. Our outcomes are still 1s and 0s. So in Bernoulli trials, these are always our outcomes. The only thing that's changed is, for success, we've now got a 0.2 probability of success, and our failures are 0.8. So now the calculations just look a bit different. So it's 0.8 times 0.8, 0.8 times 0.2, 0.2 times 0.8, and 0.2 times 0.2. So let's go do those in R. You might be able to do these in your head, but all we need to do is we've got 0.2 times 0.2. We've got two instances, of course, of 0.2 2 times 0.8, just in a different order. Just to represent that, let's add those together. And the 0.8 times 0.8. Oh, help to get my multiplication symbol right here. My star symbol. So our 3 outcomes here then should be 0.04, 0.32, and 0.64. So let's go and enter those in. So 0.4, 0.04, 0.32. So this equals 0.04. This is a conjoint probability of 0.32. So 0.16 each. And then 0.64. Was it 64, I think. And of course, these 3 all still sum to 1. So let's try that on here. So if we run this with a size of, so let's change x back to 0 to 2. We will run this with a size of 2. Just use x here, but we'll change this to 0.2. What's this look like? Well, there we go. So we've got our about 0.6. We've got this about 0.6 in the 0 category, 0.32, and then 0.04. However, let's see what this looks like with our size of 10. Let's change this back to 10. And again, a probability of 0.2. Well, what does that do to it? Nothing if I don't run the whole thing. So let's run this. There we go. So our binomial distribution still has this, what we call a normal shape, but it's skewed this way. And of course, if we specified this as 0.8, it would really just be the inverse. So we can generate lots of different shapes on this graph. We've got 3 different functions, but just remember that the logic is really just these branching probability trees. So the underlying mathematics is really quite simple here. We're just multiplying along the trees. We're summing equivalent answers together to get conjoint probabilities. And then we are expressing that in the form of a probability distribution. Or if we're using our binomial, we're of course simulating that distribution by generating random numbers. So that's all there is to the binomial distribution. So really you just got to get your head around these functions and their options. And then the rest of this, saving in framing, this is stuff which we have talked about before. It's not really part of this these questions on probability, but nonetheless, the binomial distribution is pretty easy, hopefully, both mathematically and in terms of coding, to get your head around. So in the next lab, I'm going to talk instead about the normal distribution, which adds a few more complexities, but there's also some more interesting things that we can do with it.